Welcome, everyone. Welcome again to those of you who have been attending throughout the pandemic, and welcome to any newcomers, especially our colleagues from CU, and to today's guest speaker, Dr. Jennifer Kay. She's a professor in the Department of Atmospheric and Oceanic Sciences and a fellow at CERES, both at the University of Colorado, Boulder. She's also a visiting scientist at the National Center for Atmospheric Research, NCAR. She earned her PhD at the University of Washington in 2006 and was awarded an ASP postdoc at NCAR and then a scientist position before moving down the hill to the University of Colorado. She's received numerous professional awards, including the AGU Turco Lectureship, the AMS Houghton Award, an NSF Career Award, and the CESM Distinguished Achievement Award. Dr. Kay is well known for her work with observations and models to understand climate change and variability. Her paper on the CESM Large Ensemble Simulation Dataset has received over 1,000 citations. Her research focuses on understanding the influence of radiation, clouds, precipitation, and sea ice processes on globally coupled climate system. And I'll let Jen take over from here. The mic is yours.
Great, thanks so much for the invitation, and I'm excited to share some work with you today. The talk, How Do Clouds Affect Global Warming, is very general and it's kind of pitched pretty broadly. So hopefully there'll be something there for cloud experts and cloud newbies alike. So I'm going to share my screen and start with the talk. Okay, so the context for clouds and their influence on global warming is really the large increases in CO2 and other greenhouse gases, which are, of course, driving warming at the surface all over the planet, but particularly in the Arctic. And we'll see that discussion today in the context of how clouds might influence this warming and how they make feedback on the system to amplify or dampen the warming. The Arctic is particularly notable because of the large changes in the surface ocean, where we had large areas covered with sea ice. We now have open water. 2012 and 2020 pretty closely tie each other for the least amount of Arctic sea ice in late summer. And these dramatic changes are of interest, and one might ask, with all of this newly open water and the fact that most of the world's oceans are covered with clouds, have we changed the cloud cover in the Arctic as the Arctic sea ice has retreated? So today, as I said, how do clouds affect global and Arctic warming? That'll be what I will discuss. So this topic has been reviewed by many, and I encourage you, if you're looking for an overview of some of the key papers and processes, to check out the last IPCC report, AR5, which had an entire chapter dedicated to clouds and aerosols. It was the first time in these assessments that an entire chapter was dedicated to clouds and aerosols. And in that chapter, there's a lot of discussion of some of the kind of broader background that I'll give today. I will note that the next assessment report also has an entire chapter on clouds and aerosols. And one of the things that I think is kind of notable is that we've made a lot of progress understanding clouds outside of the tropics since the last IPCC report. And so I'll summarize some of that work here today. So starting very generally, how do clouds affect the mean climate? This is often measured with the cloud radiative effect, which is just the difference between the radiation in an all sky situation and a clear sky situation. And you can see in the global mean, clouds cool the climate by about -21 watts per meter squared. And that cooling is evident over much of the globe. Of course, the influence of clouds on the radiation and energy budgets of the planet have multiple components, the shortwave and the longwave radiation. And we can see the shortwave radiation influences what leads to this cooling. So clouds are reflecting incoming sunlight, and that is leading to the planet being cooler than it would otherwise be. But clouds also, like greenhouse gases, absorb and emit long-wave radiation. And so there's also a long-wave warming influence of the clouds, which is not quite as large. You can see in some regions, the long-wave and the short-wave almost balance each other. So if we look, for example, in the Western tropical Pacific, the net effect of these two components, the short-wave and the long-wave, is pretty close to zero. But in these regions, for example, right off the west coast of the US, where you guys are, many of you in California, very strong cooling from the clouds. And that is because these are primarily low clouds where the shortwave radiation dominates. So this influence of clouds on radiation kind of leads us to think about how radiation might change in a warming planet. And for that, I'll just provide a very simple feedbacks primer for those who are not used to thinking about radiative feedbacks. So basically, what happens is we apply some sort of forcing here in watts per meter squared, and that could be due to, for example, increases in greenhouse gases such as carbon dioxide, but also due to other forcing agents such as aerosols. And that forcing is then balanced by a change in the surface temperature. So if we increase greenhouse gases, we're going to increase the surface temperature, and then we end up with basically at equilibrium, this term on the left-hand side here becomes zero. So the amount of surface warming that you get for a given forcing in watts per meter squared is a result of the feedbacks, and that can be estimated here through a feedback parameter. Here you can see it's divided up into a number of different feedbacks. And this has units which you can infer from the surface warming and the forcing of watts per meter squared per Kelvin. So a lot of what we're thinking about when we're thinking about how much warming we're going to get when we increase greenhouse gases is trying to understand these feedbacks because they basically help us translate in units from watts per meter squared to the amount of warming. So these feedbacks have been documented in many papers. The largest feedback is actually the Planck feedback, which is a negative feedback, here called the temperature feedback. We know the water vapor feedback is very large and positive, almost doubling the amount of warming that we get for a given forcing. And then on the right-hand side here, we have the cloud feedback, and the albedo feedback, and the net feedback. And so the albedo feedback, the loss of bright surfaces at high latitudes, that leads to more absorption of shortwave radiation. And so that's going to lead to more warming. So that's in general positive feedback. But the cloud feedback and the net cloud feedback here has a very interesting spatial structure. And this is just the mean across a number of CMIP-5 models. So it's really important to ask, are these feedbacks, are these what we expect to get as we continue to warm? So the average climate model global cloud feedback is positive. But of course, there's regions of the planet where the cloud feedback is in fact negative. And we'll revisit this, especially this negative feedback over the Southern Ocean, because this is one of these areas where there's been a lot of progress since the last IPCC report in understanding some of the physical processes that are generating this feedback. So it's important to emphasize that cloud feedbacks and climate models are uncertain. They're often cited as the leading cause of differences in the amount of response that we see in climate models in response to forcing. And so here, this is just a summary of that, again, from the last IPCC report. And we can see here, clouds, while the mean feedback is positive, there are models that have negative cloud feedbacks in the global mean, and the level of confidence here, we think they're likely positive. the cloud feedback is likely positive. It likely enhances the warming, but it's not as in high confidence as we have in something like water vapor and lab straight feedback. And aerosols here, I won't spend a lot of time talking about aerosols in the talk today, but obviously aerosols are quite important for cloud formation and precipitation. But here, in terms of their net forcing, that's pretty small in terms of watts per meter squared. So this low confidence, I think if I were to look at this chart, I see the place for the most opportunity to try to reduce our uncertainty is in the clouds here. So this is a schematic that appeared in the last assessment report, just showing the latitudinal distribution of processes that affect cloud climate feedbacks. And there was some color coding of that, where there was high confidence, they were put in red, and where there was low confidence, it's mostly in gray. And we can see from this cartoon some of the processes that are important for why the global cloud feedback is likely positive. The first are the rising of high clouds. This is the results from the fixed anvil temperature hypothesis, which we'll go through. The second is from subtropical low clouds, which tend to reduce the amount of shortwave radiation that they're scattering. So in a warming climate, that means there's less shortwave cooling. But there's a lot of mechanisms associated with these low clouds. And so we'll see that come through is still an area of a lot of research. And then finally here at high latitudes, we see more polar clouds. And this is something we motivated at the beginning, these large reductions in the Arctic for the amount of sea ice cover, and maybe that provides sort of a lift on the cap and the source of moisture. But I think one thing that's really important that we've learned is that there's a strong seasonal dependence to the cloud response to sea ice loss. So I'll go through these different mechanisms that lead to positive feedbacks. Here we just have this, again, the net cloud feedback. Now we have the feedback broken up into the long wave cloud feedback and the short wave cloud feedback. And you can see that the long wave cloud feedback is positive. For example, we can see here along the intertropical convergence zone where we have deep convection, there's definitely a positive feedback here. So what are the processes that are driving this positive long wave feedback? Well, this results, as I said, from the fixed anvil temperature hypothesis. And basically what we see is that with warming, the isotherms in the atmosphere move up, the convection deepens, but the temperature of the cloud top actually remains constant. And because the cloud top temperatures don't warm in step with the surface warming, the surface is warming and the tropics are actually becoming less efficient at radiating away heat. And so as a consequence, you have a positive cloud feedback. And that's just what this says here. High clouds acting as a positive feedback on climate. And this comes not only from simulations of the global climate models, but also of much higher resolution models. So here from a paper by Quang and Hartman, we can see basically what happens when we just run experiments where we increase the sea surface temperature and watch what happens to the cloud. And so you can see as we go to warmer temperatures, the cloud top here is moving up in altitude. But what's important is that the temperature at which it's radiating to space is actually staying relatively constant. And so that's, again, what's behind this positive long wave cloud feedback. What about the subtropics, these low clouds off the coast of California? I'm sure many of you are familiar with them. There's definitely thinking that the low cloud amount might decrease, but there's a lot of speculation about what the mechanisms are, and the complexity of these clouds is really important. And as of the last IPCC report, it really lacked a well-accepted theoretical basis for why this low cloud amount decreases. And if you're interested in reading some of the details, I recommend this review paper written by Chris Brotherton in 2015, which talks about some of the radiative, dynamic, thermodynamic, inversion strength changes that all can, lead to either stratocumulus thinning or thickening. And so it's a balance of all of these different complex processes that's important. Moving to the Arctic, we have observational evidence for seasonally varying cloud response to Arctic sea ice loss. So basically what we're seeing is during the summer, there are plenty of clouds in the Arctic, but there is no evidence for the clouds changing in response to the surface changing. And this may seem sort of surprising at first, but when you think about it, it makes a lot of sense. In the Arctic, the surface temperature during the summer is pretty constrained near the melting point, and the atmosphere above is able to warm. So while it's not as stable as when you have, a strong inversion forming in the middle of winter, it's still stable, and you do not have large fluxes of heat and moisture going from the surface to the lower atmosphere. So there's not a cloud sea ice feedback in the summer. In contrast, if we look in the non-summer months, here just looking north of which is now known as Utqiagvik, we see these roll clouds, an evidence of strong coupling between the surface and the atmosphere above. And this is because, of course, as we go into the darker months in the Arctic, the surface, if it's still open water, is much warmer than the air above it. And so that drives this convection and this mixing and large transfers of moisture from the surface to the lower atmosphere. And that drives this positive long wave non-summer cloud sea ice feedback. So here I'm just kind of describing in words some of the relevant processes, but we've looked at this in a number of data sets. I think one of the most interesting and compelling data sets for studying Arctic cloud processes in particular is Calypso, a spaceborne LiDAR. Calypso just celebrated its 15th birthday. It was supposed to be in space for 3 years. It's a pretty incredible mission. So here, this is just some cloud profiles during the summer and during the fall based on the Calypso observations. And we can see when we look over sea ice and over open water in the summer, the cloud profiles are basically on top of each other, suggesting that there's not a cloud response to the change in the surface cover. Whereas in the fall, we see this evidence for more low-level clouds over the open water, consistent with this positive long-wave cloud feedback. So let's return to thinking about this negative cloud feedback at the mid to high latitudes, in particular in the Southern Ocean. Why does this feedback exist? And in part, this exists because there's a lot of clouds at those latitudes, low clouds, that can change phase. So as the clouds change phase in a warming world, they go from ice to liquid. In general, liquid clouds are more reflective than ice clouds, so that leads to a negative feedback. And so we can see here just in a study where we try to separate the influence of the positive surface albedo feedback due to sea ice from the feedback due to clouds. We see this negative cloud feedback at the high southern latitudes. And in this particular model, it is associated with a change in the thermodynamics, and in particular in the cloud phase. This is of concern because one of the things that we know that's very tricky to do well in a climate model are mixed phase clouds, and understanding how to predict how much supercooled liquid are in the clouds. And if we look, we have on the bottom here observations from Calypso, again, the spaceborne LiDAR, which gives us maps of where liquid and ice clouds are based on the observations. And we can see on the top, this is just the atmospheric component of the one of the US climate models, the CESM, and we can see some really stark differences in the ice cloud at these high southern latitudes, where the model is predicting all of this ice cloud, whereas the observations are showing very little ice cloud. So that's concerning, because what that means is that basically this model may have a negative cloud feedback that's associated with the transition from ice to liquid that's too strong, because it has too much ice to begin with. So yeah, this really stark difference in the amount of ice cloud and also supercooled liquid cloud was something that really motivated a number of us to start looking at the processes in these Southern Ocean clouds and trying to understand how to do a better job to match the observations better, because the mean state here definitely has the potential to influence the feedback. So this is a story that came out last February. Climate models are running red hot and scientists don't know why. The simulations used to forecast warming have suddenly started giving us less time. So this headline came out actually in response to the newest generation of climate model simulations, some of which had equilibrium climate sensitivities, or just the amount of warming you get for quadrupling or a doubling of CO2 that were degrees higher than what we had seen before. And so this, I think, is a really catchy headline, and one that I think we should think about. One of the reasons was exactly this concern that was expressed, that many of the models had too much ice at the high southern latitudes. And so they had basically this negative optics feedback that was basically too strong. And in the newer generation models, in the CMIP6 models, what we saw is that we started to have more liquid and less ice. And that is one of the reasons that we had such a large increase in the equilibrium climate sensitivity from CMIP5 to CMIP6. So just getting to this, CMIP6 is warming more than CMIP5 due to this negative climate feedback basically weakening. And we think this is probably more realistic. And there's a nice paper by Mark Zelinka that came out earlier last year that really discusses the processes that are important. And these Southern Ocean cloud feedbacks are definitely an important reason for why the climate sensitivity increased from CMIP5 to CMIP6. So this phase change of the clouds at high southern latitudes is an interesting question and an interesting one to kind of grapple with. We talked about this optics feedback, where basically liquid clouds are more reflective than ice clouds. But there's other aspects of this that the phase and also the precipitation can be important for these clouds. So we also noticed this, and this is something I teach our cloud physics class, the graduate level cloud physics class at CU, and this was something that just really popped out at me when I was teaching this last year. It's just, we talk about how hard it is to initiate precipitation in the absence of ice. Without ice in the clouds, you need a lot of, collision, coalescence. With ice in the clouds, clouds precipitate a lot more readily. And in fact, most of the precipitation on our planet initiates in the ice phase. So this got us to thinking a little bit about the fact that some of these low cloud regimes in the Southern Ocean are going to go from regions where you might have ice to regions where there's maybe just liquid as the climate warms, that there may also be a negative lifetime feedback here too. So does this happen? Is this feedback underestimated or overestimated? And can we constrain it using the observational assets that we have? CloudSat and Calypso could be really great for that. And CloudSat's a spaceborne radar. It measures precipitation. Calypso, spaceborne LiDAR, tells you the phase. So we have all the ingredients to kind of see what might be going on in these clouds. So this leads to a paper that's actually in press right now at Nature Climate Change. It'll be coming out shortly. led by Johannes Mulmenstadt, and I'm a co-author with all the folks who are listed here. But basically, what we found was we think that this cloud lifetime feedback is underestimated likely in climate models. So why do we think that? One of the reasons we think that is because warm rain is really too efficient in most climate models. So Graham Stevens wrote this paper in 2010 called The Dreary State of Climate Models, basically suggesting they're always precipitating, you know, light precipitation is overestimated. Well, this is important because remember this cloud lifetime feedback, what we're talking about is a contrast between how efficient warm rain is versus cold rain. And if the model is just always precipitating, always raining, always, then you don't have that contrast. And so then you're not going to have this negative cloud feedback resulting from the lifetime changes properly represented. So Johannes did a very heavy-handed climate model experiment where he basically reduced the warm rain efficiency in the ECOM climate model. And what he was able to show was that this strongly affected the negative lifetime feedback and in fact made it much more negative. So, you know, now we're talking about something that's kind of going the opposite way of the cloud phase feedback that we started with. So just as a summary, because I think this is a very active area of research in terms of thinking about how transitions from ice to liquid under global warming might affect clouds. We saw this negative optics feedback, you know, for a fixed cloud condensate amount, liquid's more reflective than ice. And the idea here is that this was probably overestimated in the last generation of climate models because they had too much ice in them. But CMIP6 has less ice at the high southern latitudes, and that that has actually resulted in this feedback weakening. So we've, in a sense, leading to larger equilibrium climate sensitivity. But this is not where this story ends. We also have this negative lifetime feedback where warm precipitation is less efficient than cold precipitation. So basically we expect the warm clouds to stick around longer. And it seems like this one is probably underestimated because the warm rain is too efficient in many models. And as a result, we're thinking maybe both CMIP5 and CMIP6 models should have maybe warmed less. So it kind of returns us back to this quote, you know, climate models are running red hot and scientists don't know why. I mean, there's a lot that we do know and we are understanding, but the clouds and the precipitation and their interactions with aerosol, I think, remain something that's very, very challenging for us to constrain and a very active area of research. I don't know if you saw this joke, the XKCD, they had types of science papers and people have been doing all kinds of memes about them, types of climate science papers, one of them. And I just like this because, you know, I really like clouds and I think clouds are great. And, you know, there's a lot of papers that end up in climate science and basically it's clouds are really complicated, right? Like that's we need more data, sure, maybe we could block the sun. You know, 100,000 scientists work for 3 decades and we still have the same answer. You know, there's some things that are different, but clouds are really complicated. And so one thing you might think is, well, maybe we should try to get rid of them and just see what we understand about the system if we just disable their radiative feedbacks. And one thing that's kind of interesting to look back on is, you know, the first climate models that were run, they had clouds that were not interacting with the climate system. And so, you know, if you look back to papers, for example, by Manabi and Stouffer in the early 1980s, you know, they saw global warming, they saw associated sea ice loss and Arctic amplification, and in the absence of any kind of cloud feedback, because those processes just weren't represented in the model. And, you know, to be fair, they also had to be very judicious about what they put in the models, right? These early climate models were run on the supercomputers of their day, you know, with about 0.5 megabyte of memory. So, you know, things have really changed a lot. And so we really have the opportunity to try to model cloud processes in a totally different way now. But one of the things that my group has been doing a lot of recently is actually cloud locking. And the idea here is to just disable cloud radiative feedbacks. And we do this in the radiation module of the CESM, the climate model. And we basically are making it such that the cloud feedback does not interact with the radiation. So I think this is kind of a fun thing to do because it helps you understand the influence of clouds on the system. And we had a paper that came out last year led by Eleanor Middlemas, who's a former postdoc in my group, trying to look at quantifying the influence of cloud radiative effects on Arctic surface warming using this cloud locking technique. And the research question we were trying to address in this paper was, what is the influence of cloud radiative feedbacks on surface-based warming in a modern Earth system model? And what was kind of new about this is that we disabled the cloud feedbacks. We disabled them both regionally, so just in the Arctic, and also globally. And by doing that, we can actually isolate the influence of just the local clouds here, so just the Arctic clouds, and the global cloud feedbacks. So we ran 6 experiments here, and we have a control, 1850 control run, pre-industrial control. Then we doubled CO2, and so we looked at that. And then we ran 2 additional pairs like that, one with global cloud locking, so that's disabling the cloud feedbacks everywhere on the planet. And then these ACL runs, Arctic cloud locking, where we've only disabled the cloud feedbacks from 70 to 90 north. So what we saw, key result, the global cloud feedbacks increase both global and Arctic warming by about 25%. So this is consistent with clouds being a positive feedback on the climate system. So when we remove them, the system warms less. We can also see, sort of interestingly, that the Arctic amplification, just shown here as kind of the warming divided by the global warming, is not all that affected. So it's just appears to be some sort of 25% scalar. If we look at the Arctic cloud blocking experiments, again, where we've just disabled the clouds in the Arctic, what we see is really a negligible influence on both the Arctic and the global surface warming. Now, Arctic clouds having a small influence on global warming makes a lot of sense. The Arctic is a relatively small domain. You know, it's not a large area of the planet, so you'd have to have some pretty crazy cloud feedbacks up there to have an influence on the global mean temperature. But we were a little bit surprised that these clouds had such a small influence in the Arctic, where, you know, maybe we would expect to see more clouds over sea ice, a positive cloud feedback. We know the model has those kinds of interactions and can reproduce the observed kind of cloud response to sea ice variability. We also saw that cloud feedbacks do not alter the seasonality of Arctic surface greenhouse warming and amplification. So, you know, this pronounced seasonality where we have the most warming in sort of late fall and early winter and very little warming in the summer, which makes sense. That's when you're just melting everything. The clouds are not shaping that kind of spatiotemporal fingerprint of Arctic amplification and warming. So with any modeling study, it's always important to ask, you know, what do we know about this model and the processes that are in it? And is this model sort of fit for task for answering the questions that we're trying to answer? And so, you know, this model we're using is a well-vetted state-of-the-art Earth system model. It actually ranks really well in terms of its global performance for temperature and precipitation. And it can do things in the Arctic that are quite reasonable, like reproduce the observed Arctic sea ice loss, reproduce, as I said, these kind of cloud sea ice interactions. So that seems great. But the one thing we do know about this model is that it's also has a cloud phase issue. Notably, it really underestimates the high latitude supercooled cloud liquid. And as a result, you know, we have some concerns about whether or not the cloud in this model is having a big enough influence, and in particular, if it changes and there's cloud radiative feedbacks, if it would have enough of an influence. So we're still interested to pursue this work and try to understand the influence of Arctic clouds on warming, and this idea that maybe they don't have a big influence on the warming. We kind of want to check it with a model where we have more supercooled liquid in the clouds. So just a quick summary of this work that we've done. We've seen that the global cloud radiative feedbacks increase both global and Arctic surface greenhouse warming. In this model, we saw the Arctic cloud radiative feedbacks really didn't do very much at all to the warming in the globe or in the Arctic. But also, we know that the influence of the Arctic cloud feedbacks are likely underestimated due to a lack of high latitude supercooled cloud liquid. And more broadly, I think this type of work using a model and disabling some part of it is a really nice way to kind of probe the system and try to understand how clouds are interacting with the environment. And even if it returns us back to, for example, the earliest climate models, Manabe and Stouffer 1980, I think there's a lot we can learn by actively tinkering and hypothesis testing within these models. So with that, I'm just going to leave it here. I guess not a full hour, but I know everyone's usually a little fatigued by Zoom, and I know you all are nearing the end of your academic semester. So thank you for the invitation, and I would be happy to take any questions that you have.
While our people are getting their thoughts in order for questions, I wanted to note that Jen is actually on sabbatical and kindly agreed to spend some of her precious sabbatical with us. And I already see a hand raised from Eric Saltzman. So Eric, please unmute yourself and ask your question.
Can you hear me okay?
Yeah.
Okay, so all kinds of interesting stuff in here. Like, I could think of a million questions, but I'm going to ask one that's slightly standing back a little bit. That is, it seems to me that you've made a really compelling case that you can predict that predictability will increase. You can kind of say with confidence that the models are going to get better in a couple of decades when they're warmer and when multi-phase clouds are less of an issue, when there's less ice on the planet in these clouds. Is that true? And if so, is that a powerful thing to be able to say?
It's really interesting. I hadn't thought about it in that way, mostly because I think we're still transitioning from this kind of world where we do have a lot of ice in the clouds to one where we wouldn't. I do think that the Southern Ocean cloud regimes are ones that were neglected and not really thought about much before. And I think your point may apply there, that they may be easier to do when you get in a much warmer climate, and the storm tracks the low clouds in the storm tracks are more dominated by just liquid processes. Yeah, fascinating.
Good news for modelers. All right, I see a graduate student, Tian Yao, I think your hand was up first, and then we'll move to Juan, and then Anne-Marie.
Oh, okay. I really like this talk, and because I'm not really familiar with the clouds, I wonder, like, what if, I know clouds got like millions of cloud schemes out there. So, what's your take on, are all these cloud feedback, like this spectrum is caused by the cloud scheme itself, or it's caused by the atmospheric dynamical core itself, or is the ocean, like what would be your guess?
In terms of where the biggest uncertainties lie?
Yeah, it's like from the scheme itself or other components.
Yeah. I think I personally feel like there's a lot going on with the cloud microphysics and kind of the detailed processes of the clouds themselves. And the dynamics are certainly important. We know clouds form and evolve at scales that we're not representing in most models right now. So yeah, I think those are both really big challenges right now. One thing I will say that I think has been solved and is kind of interesting is in the IPCC, the AR5 cartoon, there was this big mention of the shift of the storm tracks. One thing that I think we've learned since then is that the shift of the storm cloud track doesn't actually have that big of an effect on the clouds. It affects where the precipitation will fall, but we don't. Initially, when we saw these kind of like, you know, shifts in where the clouds were, people were thinking it was due to the storm track shifting. But in fact, it was more thermodynamic. It was driven by where clouds were above and below 0 degrees Celsius, which I think is an interesting evolution. Yeah.
Okay. Thank you.
Yeah.
All right, Juan, please unmute yourself and ask your question, and then Anne-Marie, you're on deck.
Hi, thank you so much for the talk. I found it really interesting. Something I didn't really pick up on was, and you mentioned in your models, you essentially turned off the feedbacks from clouds. Can you kind of elaborate on that a little bit more and how it differs from just assuming a cloud-free atmosphere, I suppose?
Yeah, so that's an important point. There's still clouds there. It's just that they're prescribed to always be the same. So what we do is we run a model year, we save out all of the cloud feedbacks, and then, all of the cloud fields, not feedbacks, all of the fields. Mm-hmm. And so, you know, there's, you know, the ice, the liquid, the sizes, all these things. And then when the radiative transfer model goes to do its calculation at every time step, instead of using the clouds that the model has produced, it just uses the clouds that we have in kind of this offline file. Okay. So there's still clouds there though, and that's really important because one of the reasons that clouds are important in the Arctic, and this is just an example of how just having clouds there is really important in addition to having them feed back, is that they block the surface, they mask the surface. Right. Yeah. And so, and the Arctic, you know, I would say, you know, if you think about the top of atmosphere albedo and what's dominating it, it's mostly the atmospheric opacity, the clouds. So just having the clouds there, even if they're not interacting with, for example, the storm tracks or the sea ice, still has a large influence on something like the surface albedo feedback, for example.
Thank you.
Yeah.
All right, Anne-Marie, you're up.
Thanks, Jen. That was a really great talk, as always. So I wanted to ask you a question about your negative optics feedback, and you were really precise every time you mentioned it. And on your slides, you would say, for a fixed amount of condensate amount, liquid is reflecting more than ice. And so I wanted to ask you about that fixed condensate amount. Yeah. My impression from observation so far is that specific humidity over the oceans is going up. Over the lands, the relative humidity is maybe going down, but it's like very, very variable. And so I wanted to ask you about that assumption and what your thoughts are on that.
Yeah, well, so in a warmer atmosphere, you're going to have more water. So if all the cloud processes stayed the same, the clouds would get more reflective, right? Yeah. So I guess that's the piece that is kind of pulled out of this kind of optics feedback part of it. We wanted to separate that out. How in practice you would measure that, I think, is an interesting question, and I don't have a good answer to. I wonder.
I have no idea. Yeah.
But yeah, certainly we think that could happen, right? I mean, yeah.
Yeah. Okay. All right. Thank you.
Yeah.
All right, we have another student, Jinyuk, and then Michael Prather, you're on deck. Unmute yourself, please, Jinyuk.
Oh, whoops, sorry. Hi, Dr. K, that was good, great presentation. I just had a question. It's like, have you thought about like the wildfire impacts on cloud feedbacks and things like that in the Northern Hemisphere or just like the high mid-latitudes to high latitudes? That was kind of just my question. Yeah.
I haven't thought much about that, but I will take the opportunity to advertise the work of a PhD student who just finished at CU Boulder, Patricia. Delapontier, something like that. I always screw up the name a little bit. But anyways, she's been looking at the sea ice in the CMIP6 models. And one of the things that she noticed was some very odd trends that were happening, where there was like a sea ice recovery and then it kind of crashed after that. And she actually traced it to biomass burning aerosols, the way that the biomass burning aerosol were specified for the CMIP6 forcing. So showing that, you know, what you do for the forcing really matters for the sea ice, which is very, very sensitive. So I think this question of how something like biomass burning aerosol affect the sea ice is a very interesting one. And yeah, she just submitted the paper, but I'd be happy to put you in touch with her if you'd like to chat with her more about it. I think she just, she'll start an ASP postdoc at NCAR this fall, and that's the topic of her proposal.
Awesome, yeah, I'll email you about that later, and yeah,
Great.
Sounds good. Thank you for your response.
Okay, Michael, unmute yourself, and Mike Pritchard, you're on.
Hi, Jen. Michael Prather here. Thanks for a great talk. I appreciate it. Well, I always love tinkering with models. I'm certainly happy to dissect and do partial derivatives models. But one thing that worries me is when the system gets really messy and complex. So the question I have for you is that if you're really, you know, how do you keep the hydrology the same? Because the water vapor is probably even more important for the heating than the clouds. And so if you turn off cloud feedback, are you turning off water feedback, or are you actually having a different model, having a different rainout? So you still have to have rainout in the system. You're totally changing the water vapor, you know, the hydrology of the system, the atmosphere and the water vapor. And you think that would be absolutely a very huge one that you might have no control over, and these models might drift.
Yeah, that's a really good point. I know there are studies that have actually locked the water vapor as well. And certainly there's ways to do both of them. And that would certainly be interesting to explore. I was kind of shocked that you can turn off the cloud radiative feedbacks and you don't end up with a huge amount of drift, or just the model doesn't go off the rails. The global mean temperature does change a little bit. So it's a different mean state, but it doesn't, it's pretty artificial what we're doing, as you're exactly saying. Yeah.
Thanks.
Okay, Mike Pritchard, and then Charlie, I'm on deck.
Hey, thanks for that. Super cool. Yeah, I just have like broad questions about, I'm new to cloud locking. Like what else is like catching your attention about what comes out of it? Like there must be regional stuff like denying the local feedback between developing storms and their local radiative impacts relevant to extremes. Is it inspiring other cool interference experiments on like surface fluxes or other things? What are you most looking forward to in that category, or next incarnations of cloud locking?
Yeah, great question. There's a lot of interesting work going on with it. I'll just put a plug for Kevin Grice, who did some cloud blocking in the storm tracks and basically saw very little influence, which was interesting. And then we've also been doing this work where we double and halve CO2. And so try to compare, the system going to a warming climate versus a cooling climate with the clouds locked. And that's been really fascinating as well. One of the things that's interesting is we get more global warming than global cooling. And that's true both when we do have the clouds active and also when we disable them. And so there's some interesting implications there for paleoclimate, because it basically suggests if you're going to use something like the last glacial maximum as a constraint on equilibrium climate sensitivity, you better inflate it a little bit because we see more warming than we do cooling. And so looking at some of the state dependence of the feedbacks, I think there's some interesting work to be done there. But this is a tool that CESM has made available, and I'd be happy if someone wants to set up a simulation to work with you, but also Brian Medeiros, I should give a shout out to him. He's done a lot to kind of enable the community to do it.
All right. I'm interested in cloud amount, which cropped up in a few guises in your talk, for example, lifetime. And it's a separately observable feature of the climate system that we have a long track record of trying to measure, going all the way back to ISCIP. And So all of the feedbacks depend on cloud amount. So we can observe it and high cloud amount and low cloud amount. You can guess that if you have good retrievals. So what can you tell us about the observed behavior of cloud amount in the anthropogenic era? And have changes been detected that are above the noise of variability?
Yeah, so I think the Arctic, I mean, that's the area that I'm most familiar with, but these increases in low clouds in the fall associated with large decreases in Arctic sea ice extent, I think we can attribute those as human-caused cloud changes. Because we know that the Arctic sea ice loss can't be explained by natural variability alone. And so if the clouds are responding to the sea ice, then they're, in a sense, we've made the Arctic more cloudy. I know there's other papers that have tried to look, for example, at the fat hypothesis, so the rising cloud tops. I'm not as familiar with the details of that work. I know it's looking at El Nino, and so changes in the sea surface temperatures in the tropics is also, people have tried to use that as like a proxy for global warming, and but I'm not as familiar with that work. But I think in the Arctic, we can pretty definitively say that it's cloudier because we increase greenhouse gases.
Smoking gun. And have the Earth radiation budget experiments kind of trended also above the level of variability?
Yeah, I haven't looked at it as much from the radiation standpoint, and that's actually something that my student Jonah is working on right now, trying to look at things. Obviously, it's much harder to have a sense of what's going on at the surface from the radiation budget perspective, because we just don't have, instruments. Some, as we discussed this morning, over Greenland, but over the Arctic Ocean, it's pretty sparse. So my strategy has been more to try to look at things that we can observe really well, like from Calypso, spaceborne LiDAR, and then try to infer what they would mean for radiation when we don't always have the direct observations at the surface. But like, how big is the long wave cloud feedback you're talking about? Like that those are questions that I think are still pretty hard to answer.
Okay. Well, thank you not only for your amazing talk, but also for your efforts in the community to train students in workshops and your contributions to variability studies in general with a large ensemble that many people at UC Irvine have used and learned from. And have a great rest of your sabbatical. And let's give Jen one more round of applause.
Thank you, and thanks for being here today. I know it's a lot of Zoom this semester, so.